Hello, in this podcast we're going to be learning about toxicology, and our objectives are to describe the types of chemical hazards that we will face, and we're going to explain how we evaluate and deal with chemical hazards. One historical place where we really saw the effects of chemical hazards was in 1984, where there was a chemical leak in Bhopal, India. A cloud of toxic gas was released from a union carbide pesticide plant, and that descended on the city of Bhopal. 2,000 people were killed instantly, thousands more died later, and overall 578,000 people were affected. And people are still affected by it today, and the lawsuits of that went on for decades. Now, toxicology itself is the study of poisons and their effects on living systems. Dangerous chemicals are divided into two broad categories. First is if they're toxic, that means that they're poisonous. That can be very general or very specific. And these chemicals can be harmful in very dilute concentrations, sometimes even in parts per million. Or chemicals could be hazardous, meaning that they are just dangerous. They could be flammable, they could be explosive, they could be an irritant, acidic, or caustic, which is very similar to being acidic. There's also the field of exotoxicology, and that deals with the interactions, transformation, fate, and effects of natural and synthetic chemicals in the biosphere. Now, this next section in this podcast, we're going to be looking at types of toxins. The first category of chemicals that we're looking at here are carcinogens. A carcinogen is a chemical that can cause or promote cancer. And cancer is a disease where malignant cells reproduce uncontrollably, and the tumor that they form can squeeze organs, and that can lead to damage and possibly death. And examples of carcinogens are benzene, formaldehyde, and it doesn't have to be chemicals. It can be things like gamma radiation, X-rays, which are very energetic forms of electromagnetic radiation, PCBs, radon, certain chemicals in tobacco smoke, ultraviolet radiation, and vinyl chloride. And the difficulty thing with carcinogens is that 10 to 40 years may elapse between the initial exposure and the symptoms. Most things that are carcinogens are also mutagens. And mutagens can cause mutations or changes to DNA. And if they're in the wrong place, they can lead to cancers, and they can also lead to other disorders too, like birth defects. And a lot of mutagens can also be teratogens, and teratogens can cause birth defects that are not heritable. Alcohol is a teratogen, and that can cause low birth rate, physical, mental, and developmental problems. And I mentioned PCBs before as a carcinogen, and PCBs have been a major problem in the upper Hudson River because the 1940s to the 1970s, General Electric used PCBs as an insulator and a fire preventative. And they dumped as much as 1.3 million pounds into the Hudson, which at the time was entirely legal. And the PCBs, which are short for polychlorinated biphenyls, they are now known to be both a carcinogen and teratogen. The Hudson River is being cleaned today, but even though it's still being cleaned, even after it's being cleaned for all of this time, it still is not safe to eat the fish in the upper Hudson today. And even here in the lower Hudson and around New York City, anyone who is pregnant, anyone under 15, should not eat any fish caught in the Hudson River. Anyone else should not, they can eat what they catch, but they shouldn't eat more than one fish a week. Another category of toxins are those that affect the immune system. First one are allergens, and these are ones that cause allergies. And these are harmless substances, and they are attacked as if they are pathogens. Pollen is probably the most common example of this. Also, formaldehyde sensitizes the immune system. So besides itself being an allergen, it can trigger reactions to allergens. And also, other toxins are immune system depressants, and they suppress the immune system. And when the immune system is suppressed, that means that you can come down with other diseases. Examples of these are PCBs, methylmercury, arsenic, lead, and some pesticides. Then we come to the category of endocrine disruptors. These disrupt the hormones in the endocrine system. One type of endocrine disruptor are hormonally active agents, and these mimic hormones. These can cause reproductive problems. When they do that, they can be called gender benders. In other words, they can sort of make males be like females and females be like males. And they can also cause physical and behavioral disorders. Examples of these are aluminum, some herbicides, and phthalates. Also, hormone blockers can be other examples of gender benders because they can prevent hormones from attaching to the receptors. So how do we know how much is dangerous? Well, it's very hard. It can be hard to measure. One thing I'm showing here is this shows the dangers of indoor air pollution, where we have things that can be the sources on the inside, and because we tend to keep a lot of our windows closed, that will tend to concentrate a lot of the chemicals inside of the house. So things which outside may not be a problem can be a big problem on the inside. One way we can tell what's dangerous is by doing live laboratory animal tests. And this is the most widely used method. What you do here is you expose hundreds or thousands of lab animals. These are usually mice or rats because they live for a short time and their systems are relatively similar to ours. And expose these hundreds of thousands of lab animals under tight. These tests can take 2 to 5 years and cost up to $2 million. So why do we test live animals? Well, some reasons for it is that we are more confident in the results of this type of test than any other type of test because it's most similar to what occurs in us. Because if you do a test in just say like in a computer simulation, that's not reality. If you do a test in a tissue culture, there are things that you could be missing, like interactions with not seeing it in a whole system like what you'd see in a live animal. Because these live animals are much more similar to us. It's much closer to reality than what you would get. And of course, you cannot do these tests on people. That's just not ethical to do it, to test to see how dangerous a chemical is on a person. Of course, there are people who would say that it's not ethical to test these things on mice or rats or rabbits or any other types of animals. So that's a reason against doing tests on live animals. Another reason against is that the dosage could be very different. A dosage in a tiny mammal can be very, very different than what it is in a human. And also, the species is similar to us, but even so, they're not that similar to us, and they may react differently than they do to us. There are some other ways to test. You can do computer simulations. You can do tissue culture tests. You can test chicken egg membranes. And you could also test individual animal cells. Toxins can affect us in 2 different ways. There are acute effects and chronic effects. An acute effect usually occurs from a single large exposure, like carbon monoxide poisoning, like if someone has their heat turned off and they decide to heat their house using their oven, and the oven is not properly ventilated to heat the house. So if they're using a gas oven, and that releases a lot of carbon monoxide, and that gives them carbon monoxide poisoning. But if it's not that bad, then if they're given oxygen and fresh air, then the health effects are reversible. And then there's chronic effects. Chronic effects, those come from continuous or repeated exposures. It may take time for the symptoms may not be immediate. Those effects are usually irreversible. Examples of this would be lead or mercury poisoning or smoking. Smoking is a very good example of that because people end up smoking for years and years and years. The first few years that they're smoking, there's no immediate effect. It's decades later when emphysema strikes. Decades later when there's a heart attack. Decades later when there's lung cancer. One way of comparing the effects of different toxins is the LD50. And the LD50 is the dose that is lethal to half of those exposed within 14 days. And the graph you see here is called a dose response curve. And what's marked off there is the point of LD50. So for that particular drug, the LD50 is 20 milligrams. Another one is EC50, and that's the dose at which 50% of the maximum effect is observed. So which chemicals that we use in our lives are dangerous? Well, almost anything can be dangerous in the wrong dosage. Like sugar can be a poison. Like if you eat a whole bag of sugar, that will kill you. One way you can tell is this thing right here. This is called an MSDS, or a material safety data sheet. Whenever you use chemicals at work, you are allowed to, or actually more than that, you have a right to see the MSDS. If you go in a store, you have a right to see the MSDS for any chemical. Go and buy paint, you can get the MSDS for it and see it, and that will tell you the dangers with it. It tells you how to clean it up, how to dispose of it. Like this particular MSDS is for acetone, and acetone is a chemical that is found in, say, nail polish remover. Some things it says about this. One hazard about it is that it's a hazardous chemical and that's flammable. And it tells you how to put it out, that you want to use dry chemical power to put it out. Don't use water, use dry chemical power. It tells you that the LD50 on the skin is 20,000 milligrams per kilogram in a rabbit. It tells you that it's not classified as a carcinogen. It's not so pretty much, other than being flammable, acetone is a fairly harmless chemical. If a toxin is able to be detectable, doesn't necessarily mean it's harmful. With a lot of chemicals, frequently just don't know if the chemical is dangerous, because only 10% of the 100,000 registered synthetic chemicals, and a synthetic chemical is a man-made chemical. It's not natural. A chemist invented it. So only 10% of 100,000 registered synthetic chemicals for commercial use have been thoroughly screened for toxicity. And only 2% of those have been thoroughly tested to determine if they're carcinogens. For toxic chemicals, persistent chemicals are ones that tend to be a greater threat because they can last for years or even centuries. If they break down quickly, then it's not something we need to worry about for a long period of time. You see this in POPs, or persistent organic pollutants. They are found in every organism, even like in polar bears in the Arctic. They're found in children's toys and food packages. They're actually put in there. But like, even though no one's purposely brought these POPs to the Arctic, they've made their way through food chains to the Arctic so that they are found in polar bears. No bills passed this in the United States, but it is regulated in Europe. Bioaccumulation is an important concept, and this is something that was actually covered when you took living in. Bioaccumulation is the increase of concentration of a pollutant from the environment in an organism or part of an organism. So what happens is that the pollutant enters the body through respiration, ingestion, or skin content, and then it's stored in the body. It's usually stored in the fat, and it's slow to break down, and it's slow to excrete. So it keeps building up in the body as the body keeps taking it in. So the amount just keeps accumulating. That's what bioaccumulation is. And then you add that together with this next concept of biomagnification. And this was also covered in living environment. And what happens with biomagnification is that the concentration becomes magnified or increased as the pollutant goes from one trophic level to the next trophic level, as the organisms get eaten. For a toxin to be biomagnified, it must be long-lived. In other words, it must be persistent. It must be fat soluble. Like if it's water soluble, then it can just be easily excreted. It doesn't get stored in the fat. And it must be biologically active. And here you can see the bioaccumulation and biomagnification together. DDT is a pesticide, and we'll be discussing it later when we get into pest control. That can be found in water at 0.03 parts per billion. And then that gets bioaccumulated into the zooplankton at 0.04 parts per million. And then the small fish eat the zooplankton. And as they eat it, they accumulate that from their food, and then the DDT gets magnified in them. So it goes up to 0.5 parts per million. And then the large fish eat, the concentration increases to 2 parts per million. And then the fish-eating birds, like here we have an osprey pictured, eats the larger fish, and then they end up with 25 parts per million. And with such large concentrations, we ended up with some birds becoming endangered because their eggshells were paper thin, and when they sat on those eggs, the eggs basically just cracked. That's one of the reasons why we don't use DDT in the United States anymore. Silent Spring was a book that brought this concept to the public.
Pesticides had become a way of life in post-war America, and by 1955 the country was being treated with more than 600 million pounds a year. But in 1962, the chemical industry, the government, and agribusiness were accused of poisoning the environment in a book called Silent Spring, written by Rachel Carson. Her concern was not shared by many. The most famous pesticide at the time was DDT. It had saved millions of lives in World War II by preventing the spread of disease. It was cheap, effective, and apparently safe. Following the war, DDT and other pesticides were put to civilian use on a massive scale. They worked wonders and production exploded. From 1945 to 1955, annual pesticide use on farms went from 125 million pounds to over 600 million. Soon, government agencies began treating even the suburbs with DDT.
People thought it was a good thing because they got action in solving a problem as they conceived it. They were, for example, complaining about mosquitoes, and if the spray truck came down the street, they were told to just stay indoors for a few minutes and everything would be all right. So you had the government endorsing a product, and you had the chemical industry pushing it very aggressively.
Public health departments staged demonstrations to convince the public of DDT's effectiveness and safety. Enthusiasm for the chemical knew no bounds, and few were questioning the wisdom of such use. Public places and private backyards were being treated whether people liked it or not. In 1957, planes sprayed a Massachusetts bird sanctuary owned by Olga Hudson, a friend of Carson's. In fury and desperation, Hudson told her what had happened. The birds showed all the symptoms typical of DDT poisoning. Hudson knew that the planes would be back in spite of her protests. She asked Carson for help. Carson later remembered how the thought of a spring silent of birdsong had moved her to action.
It was your personal letter to me that started it all. In it, you told what had happened and begged me to find someone in Washington who could help. It was in the course of finding that someone that I realized I must write the book.
Carson attacked what she saw as a heavy-handed, public-be-damned attitude behind certain government programs.
They sprayed truck gardens and dairy farms, fish ponds and salt marshes, showering insecticide over children at play. A quarter horse drank from a trough in a field which the planes had sprayed. 10 hours later, it was dead.
See, all the big programs prior to that were largely federal lands. This was a big federal program that began to treat private lands. including farmlands. And all of a sudden the milk was contaminated and the farmers couldn't sell their milk. And people were worried about their wildlife. It just led to a clamor.
Carson's dire warning was that by poisoning nature, people were ultimately poisoning each other and subverting what she considered a fundamental right to a healthy environment.
See, what people don't understand is that Rachel Carson wasn't for the complete outlawing of pesticides or chemicals to help agriculture. Her point of view was that it was over-abused, that it wasn't used properly, it wasn't under control.
Carson knew that the only way to bring about lasting change was to encourage government to take a leadership role. President Kennedy's Science Advisory Committee released its report. It vindicated Carson's warning and ended with this conclusion. Until the publication of Silent Spring by Rachel Carson, people were generally unaware of the toxicity of pesticides. But Silent Spring transcended the pesticide issue and forced people to think about the environment in a new way. And within a decade, sweeping environmental laws were enacted.
Another concept that we need to know are that some toxins interact with other toxins. There can be an antagonistic reaction where the chemicals react against each other so that they will interfere with each other, and if they're both toxins, that's actually a good thing. They can also be an additive reaction where they add to each other, or they can be a synergistic reaction where they exacerbate what the effect is. An example of that would be both asbestos and smoking increase the risk of lung cancer. But when you put them together, they increase the risk of lung cancer greatly. It goes from each individually, it's 20 times. Put them together, it's 400 times. And now we come to laws in the United States. In 1938, the Food, Drug, and Cosmetic Act gave the FDA the ability to regulate foods, food additives, cosmetic drugs, and medical devices. FIFRA is the Federal Insecticide, Fungicide, and Rodenticide Act of 1947, and that allows the EPA to regulate pesticides. The OSHA Act of 1970 created OSHA, which is the Occupational Safety and Health Administration, and they regulate workplace hazards. TSCA is the Toxic Substances Control Act, and that allows the EPA to regulate synthetic chemicals that are not covered by other laws. But even there's a catch-22, because while the EPA can ban substances like PCBs, they almost have to have proof of toxicity to study for the toxicity. Another law is the Federal Hazardous Substances Control Act of 1960, and that means that the hazardous household substances must have a warning label. And the Toxic Substances Control Act of 1976 allows the EPA to track industrial chemicals produced or imported into the United States. Now we're going to look at international treaties and laws. A treaty is an agreement between different countries, and a law is a law of one country. The Stockholm Convention on Persistent Organic Pollutants, or POPs, that's effective as of 2004. 140 countries have ratified it, and that ends the use and release of the 12 most dangerous POPs, and it sets guidelines for phasing out and transitioning to alternatives. And in 2007, the European Union has the REACH program, and REACH stands for Registration, Evaluation, Authorization, and Restriction of Chemicals. And what that has done is it's shifted testing for chemical safety from governments to industry. In the United States, it's still on government. What that does is it registers and regulates substances that are over 1 metric ton. Where it's less than 1 metric ton, it doesn't, and that basically allows for innovation. Now we come to our concluding questions. Number 1, what is a toxic substance? Number 2, what kind of substance is PCB? Number 3, name one reason. Number 3, name one reason for and one reason for not doing live animal testing. Number 4, what is the difference between acute and chronic effects? And number 5, what was the impact of Silent Spring? That concludes this podcast, and I will see you in class tomorrow.